So, hello everyone, welcome to the 74th Elixir Berlin edition, this time online. First time hosting an online event, so hopefully will everything be fine. So let's start with, so basically the Wi-Fi for today is your home Wi-Fi, and the password you should know. Regarding so the live session, you can see on YouTube. So here is the link. Most likely, if you see this slide, then you already know the link through the YouTube channel. All the communication and QA is going to happen on Discord. You can see the Discord link here, but I guess my head is on it. I'll try to remove it for a second so that you see the full link. The idea is that any questions that you have, please write them down in Discord, and the speaker is going to answer those at the end of his talk. So so this is the Discord. If you haven't joined it yet, please do so, because we are not using YouTube chat for any communication. And also after the event, please stay around and ask questions. The speaker will be there, and also other Elixir Berlin community people. So basically for today, the plan is that we will have one talk by Thomas. The talk's name is Don't Do This at Home, Building Your Own Distributed Data Store in Elixir. So I think Thomas can give also a slightly better overview of himself together with the talk. And I'll now give the word to Thomas.
Hello everyone, I hope everyone hear me, because setting is always what it is. So I am Thomas de Pierre, and today we are going to talk about things we should not do at home, which is kind of problematic these days because we mostly work at home. So we thank you for telling me the sound is good, you go. So it's the thing we should not do at home. Problem is we are at home. I'm still going to keep it because we are not going to stay that way all our life, I hope. So I'm Thomas de Pierre. I am a distributed software engineer, and that most of you probably are distributed software engineer, right? We write software for a living. That's what we do in this type of meetups, right? And most of our software these days target something that talks through the network to something else. So we do distributed system. And there are multiple rules that we learn when we learn how to be a software engineer or a distributed software engineer. Things like, you should not roll your own crypto. You should not use JWT without a library hiding it. You should not use SSL. We use TLS instead. In the Elixir world, we have things like, do not spawn a process without supervising it, right? Because if you do that, you can't find it nicely and it's not going to be shut down nicely. Some of the big rules that are pretty important and that we hear about a lot when we get into this kind of software and backend is that you should not implement your own database, use one that is known. And I think, I don't know for you, but in most of my life, I ended up using most of my system, I end up using Postgres a lot. And if you really have to implement your own database, like you have to use your file system or something to store your own files, please don't do a distributed one, right? You just don't. You can store some stuff with the file system, that's really bad, but don't try to distribute it, right? Because that's really hard. And so the way we do that is that we have a whole array and slew of databases that all have different goal and targets so that we don't have to do our own. Today, I'm going to break these two rules with you, and because we have to do it. But before... Warning. The action displayed in this talk were performed by so-called experts. Do not try this at home. Okay, so my name is Thomas de Pierre, and this is a story of how we build a distributed data store for, I respect, our product. So please do not try this at home, right? Like most of my talk, we're going to follow a really simple synopsis here. We're going to present the product that is going to be underpinned by this data store, so we can extract the goals and constraints we have on our design, right? From there, we are going to explain the design that was chosen and some implementation details. Hopefully there will be a bit of Elixir here, but maybe not so much, we'll see. And finally, I will try to provide you with a list of resources and things that you can use if you can do this, if you want to do this at home, or if you need to do some of this at home. But remember, I'm the expert. If some of you have problem following and all, I'm going to keep having the on the right of your screen, you are going to keep having all this information which is basically my speaker notes so that you can follow on with me. So iRespecs is a software as a service tool that allow people to explore the data produced by the data suite. You basically send us unit files and that you can get from a lot of these frameworks, and we store it and you can query it, right? That's why we needed to do our own data store, right? We needed to find a way to store these files and to query them at will, and it ended up that nothing was doing that. The query interface look something like that in our current prototype. We have added a query window selector since then, but basically you have here you get the query part. Here you get the raw data, and here you can select your columns. And here that you can see well, you can get some aggregation analytics data. The goals and constraints we add on this is that we need to be able to query on the fly, right? Basically, the idea is that you can do exploratory querying with that. You can do a research into what happened to your data and to your test. So if you discover that some tests are flaky, you want to go in, check, hey, how long have we been having flaky tests, and then you discover it was a long time ago, then you want to say, okay, which are the tests that were flaky all that time? How many of them was there? How has it evolved over time? All this stuff you will only be able to ask these questions once you have already do a query, right? So we need you to be able to have quick, efficient query so that you can explore and that you can use on anything. You can query anything on the whole data. We also want to accept any GUnit, and the main reason for that is that we don't want to have to tell you which framework we support or not. We just want to support everything and not have to handle that part. We not quotas because we have a SaaS, and that means that we need to be able to tell you you only have this numbers of gigabytes, and after that we kill some of your data, your older data. We want to do some grouping function because we need to do analytics, right? So we need to be able to tell you to count, to do count distinct, to do percentiles, to do things like average, sum, things like that. We also want to be able to return the raw data, right? So you can look at the whole thing without any analytics if you really need to understand what's happening. An interesting thing that is going to help us later is that we always query on the primary key, which is the timestamps. That's good because it means that basically we always have a query window, right? You can't say, I want all the data for all the time. That doesn't work for us. Another good thing is that we don't update any events. Once you did your test suite, right, you run your CI with your test suite, you probably are not going to rerun it again. If you run it again, it's a slightly different thing. So we don't have to do updates. That's really nice for a data store. And we don't need to do joins, right? If you send data to a data set, for example, I don't know, my Elixir project 1, you are not going to mix that with your Ruby project. That's the goal. So our constraint were pretty high. We had a really limited budget, something like 1K to spend on money, on infrastructure. We have to deal with sparse data because the GUnit can change anytime and we don't know, and the data inside of it change a lot. Like if you have a failure, you are going to get an error message, right, for your test, but the error message field doesn't exist if there's no failure. So the data is sparse, right? We have holes in the data. We want the query to be really fast. So our target right now is under 5-second return for anything. Good news is we can be AP. We don't care too much about not returning all the data. It's far more important to return data fast. We do have to handle quite a lot of data because people want to keep the history and because, well, we're doing analytics, right? So you need a lot of data for it to make sense. The schema of that data is unstable. Remember the fact that it's sparse. Not only that, people could send Ruby and Elixir stuff into the same data set, and that means that we'll have different type of data because all the GUnit implementation are slightly different. We only have 2 devs part-time, me and my friend, and we have approximately 6 months to get to launch. That's a lot of constraint, and we could not find an existing data store that would nicely handle all of this and was inside our budget to operate. Right? We tried with Postgres, the prototype was with Postgres. It basically stopped working pretty fast. And when we looked at the rest of the market, it was pretty complex. So we decided that, you know what, we are going to build our own data store. Now, the reason this was acceptable is because this was fairly limited. Our constraint and goal allowed us to really limit what we're going to do with that. So we store flat key value events, pretty wide but flat, which is why we ended up with a columnar store. We'll talk about that. We use Kafka for most of our storage distribution, and that enables us to solve a lot of the problems that would make these things untractable if we didn't have that. And all the rest of the goals that I showed you is handled in Elixir through unwritten distributed code, and for the query builder, LiveView, which really enables us to cut down our time spent building this thing because we didn't have to build an SPA. So that's basically the design we ended up with. So now let's go a bit of the detail. So JUnit. So our data input is JUnit, right? We receive JUnit. That's what most TEMS frameworks can output, and that's the common denominator. Because Jenkins use it to extract some basic analytics about what happens to your test suites, and so every test framework in the world have a way to output JUnit. For XUnit, for example, you can find a plugin online that will do it. Now, JUnit is not a nice format. It's an XML format for test suite data. It is not specified. I put badly, but the reality is that there is no specification. It is hierarchical, which means that you can go really, really nested and deep, and it is highly complex. You have dozens, and even more than that, a handful of dozens of fields that can be there or not, depending on how the person writing it decided to use it. Our engineering students take that JUnit, we accept it, we take it, you send it, we accept it, and we transform it through some pretty gnarly unroll parser in Elixir to transform it into a flat white JSON event. So basically what we do is that we take all this nested stuff and we flatten it. So we take the smallest piece of data, which is a test case, that's the smallest unit of information in JUnit, and we roll down into it all the metadata that come in. And that allows us to know for every test case, we have an event with how long it took to run, the error message, the type of framework, the type of data, the name of the test, etc., etc., etc. There is a lot of information here. And we send that into Kafka, which means that we now have a stream of events, right? And that's where our data store really begins. So we use Kafka at the heart of the distributed storage part of our specs. And so the way it works is that we use Kafka for mostly two things. First, we use it as a write-ahead logs, right? As the logs of all the events we took in, right? We have a streams of events inside Kafka. And basically, we put the JSON event into Kafka, one topic per dataset. So we use Kafka topics as a distribution of datasets. So, and a dataset is basically more or less one test suite, right? So if your team has two services, one Rails service and one Elixir service, you are probably going to have two datasets, one for the Elixir service and one for the Rails service CI. And so we just inject the event into that. The storage node at the other side basically just read the dataset they are assigned at their pace. So you just go and say, hey, Kafka, give me the latest thing that I have not processed yet. Thank you. And you store the offset and you keep going that way. We keep all the events that are inside your quota in Kafka. And that's mostly what allows us to do a distributed data store with these constraints. Because we can rebuild a whole storage node at any point by replaying the Kafka stream, right? The event stream. We do have a checkpointing and backup mechanism in it to allow to not have to replace the whole Kafka stream, but to go from a checkpoint. But that's an optimization, right? You don't need that to make it work. We also use Kafka as a distribution mechanism. Remember, we talked about the fact that storage node get assigned some dataset and they stream from that. So the way we do that, and I want to talk a bit about it a little bit, is that we use Kafka consumer groups. So Kafka consumer groups is basically a way to say, hey, this set of nodes that are going to consume the data need to coordinate together to distribute the data between themselves. And the way that works in Kafka is that Kafka divides topics into partitions, which is a natural distribution unit of Kafka. And so your consumer are going to get assigned some partitions. And there is some automatic rebalance here. If a consumer dies, there is a heartbeat that's going to check that your consumer is not there anymore, and it's going to rebalance the thing so you don't lose anything. That's great. That simplifies our setup a lot because now Kafka does all the work of handling the rebalancing and the partitions. We did have a small problem though. We always want to be able to go query, which means that we want 2 replicas per Kafka partition. That's not possible by default because the default Kafka consumer groups only allow 1 partition per 1 consumer group, per 1 consumer, right? That's basically how Kafka handles. If you have more consumers than partitions, then Kafka doesn't give the data to anyone, right? The consumers that are left over with nothing are just standby in case something happens. We don't wanted that. We wanted 2 replica always following the same partition. So what we did is that we upstream some advanced use into Broad, which is a Erlang library for Kafka, so I advise you to use. It's probably the most advanced one by Columnar. And what it does is that we use Kafka Consumer Group Protocol, which allow you to do your own distribution in the rebalance protocol. So we just find a way to define that we want 2 nodes for each partition. You write your own code to distribute the data and to do the thing. And Kafka will just call your distribution function every time there is a need, and you will tell it, okay, so I recomputed where every node, where every partition should be, here's the new things, and Kafka find a way to make everything happen. This is a fairly niche and badly documented capability from Kafka, but it allows us to avoid churn. We will talk a bit more later, but it works really well. If you have to do this kind of stuff, if you have to do a distribution of data and rebalancing of data, and you are using Kafka, please have a look at this thing because that's probably going to help you a lot. We use a columnar store to store events. This means that when we receive an event, we explode it into different columns, and we have 1 file per column. So if I have an event with an error message and a failure state, then I'm going to have a column failure state and a column error message, which are 2 different files. We do that because columnar store are greatly adapted to wide sparse data. Right? If you have a lot of data where a lot of columns are nulled all the time, that's great for a columnar store, and we will see why. There exists columnar file format already, but most of them are built for MapReduce and Hadoop, and they really not fit our need. So once again, we had to do our own. So we built our own format, and here is basically how it works. So most of our database that we know, like Postgres and all, store data by rows. But for analytical queries, that means that you have to load the whole row into memory, or at least parse the whole row when you want to extract some data. That's not really interesting because we regularly have a limited set of columns that we want across the whole set of data. So it's far more interesting to be able to directly go to a column. So here how a query works in a columnar store. The first thing you do is that you get the index. So you have a query window, you go through all your data into your index. In our case, it's a file called index.timestamp, and you get the timestamp, and you check if the timestamp is in your query window. If yes, you keep the index in a list, right? And then you take the whole list of columns you're interested in, you go open that file, and you go through it from top to bottom. And the way it works is that every row of that file is the index, right? And the data for this column at that index. And so you can just process linearly the whole file, and you just keep the data you need. So for example, if I use index 1, if I don't use index 1, then I just skip that. I go to 2. 2, this is in my list of query windows timestamp. So I extract U. I have U on 2. 15, it's not. 40, it's not, etc., etc. And what we do is that we keep this index column ordered so we can know exactly when to stop going through in our column, right? Because if we only have 2 and 3, we go 2, we don't need it. 15, that's too high. That's higher than 3 that we had, so we can just skip the rest, right? And that works really simply. That's pretty fast, and that's relatively easy to do in Elixir thanks to IO bin read and IO bin write. And we use binary pattern matching to do the custom encoding and decoding of the file format. That's what's really why, well, this is really easy. I think the whole thing is set in 300 line of code to do everything. And also all the gatekeeping, all the bookkeeping, when you store a thing, when you add things, when you delete things, everything is done in 300 line of code. It works really well. And it's pretty memory efficient because we only load in memory what we need. The other good thing with this type of store is that this works really, really well with SSD and particularly in VMI, which is pretty easy to get nowadays on AWS or Google Cloud or Azure, and that's really speed up because you now can have a speed comparable to when we were holding everything in memory without having to pay for that memory, and that's really nice. So that's all the stuff that we do. Columnar store are great because null take no space, right? Because if you go back, if I have a null here, 3 has a message of null, right? But as it's null, I can just skip it. That's one of the big things in Columnar store. I don't have to store my null at all. I can just skip them. Every query goes through a primary key, so we don't need a secondary index, which is great and simplify a lot of things, and we can do our columnar store pretty simply. We happen only, which helps a lot too. You can do columnar store with updates, but that's more painful. So we had to build our own, and that just works. It's just a FileSystem folder where we have all our column file together, right? It's pretty easy to segment by size because basically what happens is that once we reach a certain size, we just use ls to know how big the thing is. I mean du, but fine stat, to know how big the folder is. When the folder is big enough to basically 500 megabytes, we just open a new folder and we just increment the number. And so we can just go, if you're above your quota, we can just delete the oldest folder. It just works, it's easy, it works well. It supports all our queries, and basically we have 4 data type: string, which is a variable length type; int, which is a variable length type too for us; float, which is just a double, an i3 double; and boolean, which is just a basic boolean. Now, our distributed query engine is basically really simple. It's in Elixir, it's one file, and it's something like 150 lines of code, mostly due to bookkeeping stuff. Basically, what it does is that it asks Kafka for nodes holding the partition. So, this data set, I need all this data. Hey, Kafka, tell me which nodes store these partitions. We get it all. Then we fan out the query to all these partitions through task kill many. This is pretty nice because it allows us to... task kill many will automatically allow you easily to kill queries that takes too long. So if one partition do not answer for any reason, we can just after 5 seconds, the query is going to be killed, and we can go back to just giving the data we received. This is, if you do any kind of distributed stuff over multiple machine, please have a look at task kill many. It's probably going to be what you want. Probably also work for this multiple core in case you want to be AP and not CP. In case of timeout, we just drop the data for node, right? We care far more about giving back the data. Time manipulation, so the thing to keep out from all this work we did on the distributed query engine, time manipulation is a pain. It is, both on the browser and on Elixir. You have to do a lot of work around time manipulation. Our timestamp were missing milliseconds for sometimes, which means that we're not receiving any data. We had to fix that. A lot of that stuff is really not obvious and problematic. Versioning so our query engine takes the query from the live view that we saw at the beginning, transform it into an intermediary representation, and send the intermediary representation to all the partitions. What that means is that in case we do an update, right, we deploy a new version, we tend to do rolling update. And what that means is that it's possible that some of our node work with a different version of the intermediate representation than the node that sends the query. That means you have to version your intermediate representation to be sure that it always works. That's a pain. We have not done it in really well right now. And that's a generic problem with distribution on OTP systems where you need to make sure that your messages are going to work cross versions. There is not a lot of help for that. It's a lot of things you have to do by hand, and that's pretty painful. And we need commutative function to allow combining. So let me explain. If you remember, we were doing sum, count, min, max, average, percentiles on int map, right? And that means that when we distribute the query over multiple partition, each partition is going to compute this data. We could send all the data back to the main one, but that would mean storing everything in memory. And that's kind of the thing we did not want it to do by distributing, because distributing allows us to distribute the memory load, right? So what we want is to compute an intermediary result and then to combine it at the end when we collect all the queries from all the nodes we found out to. Thing is, combining aggregation function is easy for sum. Sum, pretty easy, you add the two sum. Count, you add the two count. Min and max, you pick the min or the max of both. Average is already more complex. You can't average to average, right? What you have to do is that you have to do a count on a sum for every one of them, combine them, and then divide the count on the sum, right? At the last moment. But that's still pretty doable. And to not have to special case everything into our query engine, what we did is that we made a protocol for ease of use. So we defined a protocol called aggregable, which has for function to create a new aggregable, and you pass the type of aggregable you want. An add, which is a way to add a new value inside the aggregables. For sum, it would add things. For count, it would add one count. It would increment the count. Merge, which take two aggregables and merge them together and do the right thing. For sum, count, min, max, and average, for example. And value, which take the merging and output the value expected, right? That works really well for us, and I advise people to do that kind of thing when you have multiple structures that share the same kind of access patterns. Now, we also provide three other things. We provide count distinct, percentile, and a heap map. Count distinct, probably everyone knows about it. Count distinct is pretty hard to do in a distributed manner, right? You have to, the naive way is that you keep a list of all the distinct value you encountered, and then you count that at the end. The problem is, and you can merge that as a set, you can merge a set, that's easy to do. The problem is, in our case, we can have a lot of data with high cardinality. We have a lot of different value in the same column. So that would not work, so that would blow up our memories. So what we do is that we use a trick called hyperlog-log, you can find it online, which is a statistical trick that allows you to get a pretty close estimation of the count distinct of a set, but in a way that is mergeable in commutative way. Percentile heap map are even more complex to do. They need a really complex statistical trick. There is no implementation in Elixir. Hyperlog has an implementation in Erlang. We had to patch it because it was not working well with recent OTP and recent Rebar. We'll probably release that as a next package soon. But there is percentile heap map needs a different statistical trick, far more complex. The state of the art is tdigest, and a better one I think for us is called ddsketch from Datadog, and what released last year. The paper explaining how it works was released last year, and none of them has a good implementation in Elixir. We are probably going to release an X package on that, making it happen, because we need to get it done. But we have not done it yet because it's not yet in a place where we can release an X package for that. So that's how we did it. Now, what can you keep from that on how to do this at home? First thing is, please go read, and I forgot to put it in the slide, but go read designing scalable and resilient application with Erlang OTP by Francesco Cesarini. It's especially the last 4 chapters are probably the most important for someone that does that with Erlang and Elixir, because it's going to help you design your whole cluster. The second more important thing is please know your constraint. Remember, the whole reason we were able to do this data store ourselves with our limited resource is because, one, we use Elixir, which simplify a lot of this stuff, right? We start still many, binary pattern matching, etc., etc. But also because we have pretty hard constraint. We don't have to update an event. We are append only. We only do queries for analytical things. All this stuff makes things easier. And you need to know this, and you need to use this constraint to direct your design. If you need to build this kind of application of data store or application-based data store, please go read this book, Designing Data-Intensive Applications by Martin Kleppmann. It is the reference today. It's a modern book. It's a pretty young book. And it's a reference today for everything related to handling distributed data in your application. It covers a bunch of things you will not need at all, you'll probably never need. And it's kind of shallow, right? The paragraphs do not go in big detail into every tool, but it allows you to know all the existing tools out there for every situation, so that when you know your constraint, you can pick which tool you use. it has also a lot of reference. Every chapter has like 3 or 4 pages of references for research paper and other books to go in depth. And that's the other advice I could give if you have to do this. You will need to read research. You will need to read research book. You will need to read research papers, because a lot of stuff in distributed system is not implemented anyway. Right? So the research was done. We have a good idea of how it works, but the implementation is only done in Java or in a strange C++ academic application that you cannot reuse, and you are going to be at the edge. You are going to re-implement a lot of stuff yourself. That means you are going to have to read and implement the research paper. Not only read them to understand them, but you are going to have to implement the algorithm and the data structure they talk about, and this is not easy. Which bring me to this. You will need property-based testing. And this book by Fred Ebert is the property-based testing book for Erlang and Elixir. It's a great book. I'm reading it right now. And the reason you need that is that the research papers are rarely battle-tested. They are usually not written in the language of code. Usually they will explain in a math language what they're trying to do with algorithm, but they will not have a code implementation. They're usually pretty complex to implement with a lot of edge case. That's happened a lot, especially because they have not been optimized. And prop tests will allow you to make sure that what you implemented from paper work as you want, even after you optimize it, because it's probably not going to be satisfying the way the paper implemented it, because the paper implemented it to be easy to prove. That's probably not what you want. You probably want to optimize it. And the advantage of research paper is that they will define the properties and invariants that the algorithm keeps right and what it's trying to do, which means that you can encode that into your property-based test, and that's going to help you a lot. And finally, 2 YouTube videos you can look. If you are interested in the Kafka Rebalance protocol I talked about, this video, my slide will be up. I will give the link just after this talk. You can go check. This video is about how this works, and that's probably the best documentation we have for this protocol, because it's really useful. It is there, you can use it, it's public, but it's really badly documented. And the second one is why we built our own distributed column store from Honeycomb, which was basically the inspiration from this data store we did. And on that, that's the end of my talk. My name is Thomas Lepierre. I am the CEO of iRespects, and thank you for being with me. I will take some questions. So how long have we been building and running it so far? That's a good question. We have been building it for... The first prototype was in December, but the first prototype was not using this Columnar data store. We began building this data store in April or March. And right now the whole data store things work. It has been working for months now. We are not storing a lot of customer data yet because we are slowly launching. We are still in stealth launch right now. The query engine, I was fixing some timestamp problem yesterday, so not a long time working, but it has been it has been running for 2 weeks now. So it's pretty young, but it's working pretty well for us. Time spent have been the most problematic things. Timestamp are a pain. Another question, maybe? If question are too hard, I can give the stream back and go into the voice channel with everyone. We can talk. Have a good evening, everyone. I will give the stream back to you.
So thank you, Thomas, for the talk. Please stay around. Yeah, and Thomas will be around to answer some questions if you have in the chat, and also feel free to just talk with the other watchers and members of the group. So thank you, and see you next month.